Greetings, everybody. My name is Timur. Welcome to Getting Started with exabyte-io webinar. I hope you're doing well. This is an uncertain time right now, and I hope the coronavirus situation doesn't affect you too much. And my best wishes to you and your family to stay well in this uncertain situation. We'll be speaking today about getting started with the exabyte.io platform. And here are some key takeaways before we start. The goal of this webinar is to help users understand the main concepts behind the platform. This is the first webinar in a monthly recurring series. First Friday of the month, we speak about the basic concepts, how to get started. And on the third Friday of each month, we speak about advanced topics. Every participant should be a registered exabyte.io platform user to try this functionality in action. And every participant will receive this presentation in PDF format, so no need to take notes as we speak. This webinar is recorded and will be made available online. All information contained here is also available in our online documentation. At any point during this webinar, we encourage you to ask questions. You can do that by either using the chat or Q&A window in here. And we will have dedicated time to answer those questions during the webinar today. The agenda for today is like this. First, we'll speak about the exabyte platform capabilities, our vision for it, the current functionality. And then we'll speak about the core parts of the platform. We'll understand what's under the hood. We'll speak about the common user interface components and actions that are available to the users, a little bit about the accounts and service levels too. And then we will proceed to speak about the entities that the platform operates with, such as materials, workflows, and jobs. And at the end of these two sessions, we'll have a Q&A break. Okay, so let's go forward and start with the overview of the exabyte platform. What is it really? It's a digital ecosystem for materials research and development, a digital ecosystem that brings together experts with backgrounds in multiple different scientific fields. And we think about it starting from the focal point that can bring all these different people together. And we call this focal point the cloud. It doesn't necessarily have to be a public cloud. It could be private clouds deployed on a company private infrastructure, but it's a focal point where all these different kinds of users can communicate with each other. That includes the computational sciences, the experimental sciences, the data scientists, IT administrators, and management as well. And we have to have a collection of different simulation tools that some of them can be written in-house, some of them could be commercial, some of them could be open source. And all of them have to work together to produce data that can be well organized, structured in a database to facilitate machine learning. And all of this has to be secure so that this collaboration, whenever it creates some proprietary data, doesn't leak any information outside. And that's how we see the platform itself. That's how we see the concept for it. And to implement it, we start with developing open source components. We develop and maintain a set of open source components that together form the foundation for this FAIR R&D ecosystem. FAIR is a term that stands for finding, findable, accessible, interoperable, and reusable. The data standards for the entities that we support, materials, workflows, jobs, and materials properties, are implemented in an object-oriented extendable way and are separated on purpose to improve the modularity. It's common for people that come from computational material science background to mix the information related to materials and simulation workflows, for example. And we on purpose separated at the very, very fundamental level. The data structures that represent the standards here are implemented in a widely used JSON schemas format that define the data component and their relationships. The source code is available online on GitHub. We name it ESSE, which stands for Exabyte Source of Schemas and Examples for brevity. We also built extractors which are software tools that help convert the data from existing sources into SE. And we have examples for density functional theory calculations with WASP and Quantum Espresso, also in an open source domain on GitHub. Applications allow users to utilize these data formats to do their daily work, such as create or edit materials information, set up the simulation workflows, and we also have an example application available on GitHub too for materials design. Next, we take these open source components and build the publicly accessible online platform at platform.exabyte.io. The components can be licensed and further deployed in a private cloud scenario for our enterprise customers. And we start with the computational material sciences as the most well-known to us users scenario. So people who use computational tools today through extractors, they can contribute data to our platform, which is organized in a database and can be accessed by the community that might not necessarily be computational sciences. Adding the data sciences to this picture allows to build data analytics on the data that computational sciences generate. And adding the experimental researchers as well allows to accelerate time to validation. They can see the results that computational sciences produce, they can collaborate, they can communicate with each other. Sometimes the companies that we deal with, or the customers that we deal with, they have external elements, especially for experimental equipment, right? They have laboratory equipment that we plan to incorporate into this picture in the future. Sometimes they have the internal computational resources that they would also like to incorporate, and the data platform. And that's what we call the external elements that can feed data into our platform through the RESTful API. So that completes the picture. That's how we organize the materials R&D daily tasks for different kinds of sciences. Excuse me. When we think about the digital materials R&D cycle specifically, we can identify at least 7 different components. And today the Exabyte platform supports 6 of them. That includes the design of material structures, design of modeling workflows, the logic that goes into it, provisioning high-performance computing infrastructure, controlling and asserting the completion of these calculations, collecting and organizing data in a structured database, and building data analytics onto artificial intelligence tools. 7th component to feed experimental validation is what we're working on, and it's going to be added in the future. So here's how the platform looks to the end user. This is an example account, our team account for exabyte.io team. You can see that there are multiple people collaborating within that account, and there are multiple entities like materials, workflows, and jobs that are available to each of these account members. Depending on their permissions, they can do different actions. They can edit or just view some of these items. And we can see which infrastructure is available to this account from the snapshot as well. As we went through the R&D cycle, this is part number 1 of it, when we design materials from atoms up. And here you can see a quick example of how we can design a surface, semiconductor interface, semiconductor surface for indium, aluminum, gallium arsenide in this case. We can save this information in a database and add a tag so that we can quickly find it in the future. Beyond just the single structures, we can also code in chemical reactions. And in this case, I'm demonstrating an example chemical reaction where an atom of hydrogen is moving within the strontium zirconium oxide matrix. And here we see that the atom is moving along a certain path. And we can start with the initial configuration and go to the final to represent a particular chemical reaction. Okay. The second part is when we execute, set up and execute the simulations to predict the properties of this newly created structures. And for that, we have a workflow designer, a representation in a graphical user interface, and a set of template workflows. So these template workflows come from either curators of the platform or from the user themselves, and they can be selected in a simple way and applied to the materials that we have just designed. we also need to set up the computational infrastructure for it, and I will speak about that in more details a little later. So here we have the calculation that is prepared, where we have a certain material and a certain kind of simulation workflow associated with it. The next step is to execute it and make sure that the calculation proceeds forward and finishes successfully. So for that, we also have the machinery to do that, to demonstrate which unit is active right now, which unit is running, make sure that the convergence is done properly. And at the end, we present users with the result, which in the case of a chemical reaction, for example, is the chemical reaction profile, where we can see the barrier and the transition state as an example. Oftentimes, the people who run these calculations on a daily basis, they want to have programmatic access instead of going online and clicking on buttons. They want to do these calculations programmatically. And that's what we support as well. So here you can see multiple windows. This is a Python code. This is the platform. So the code will be executed and the platform will demonstrate the changes, right? So here what we do is we create materials on the platform, create calculation jobs for these materials with a certain workflow. And as you can see here, then we wait for the jobs to complete, and we extract the information out of the calculations that these jobs are producing to form a pandas data frame. And then we will use this pandas data frame to create a machine learning model, for example. But this is just a quick demonstration from a Python script programmatically. We also support Jupyter notebooks. So here's how one can open a Jupyter notebook. We need to start the Jupyter application in the same way as we would start any other simulation, and then open the notebook to edit it in real time. And here is an example of how we can communicate with our RESTful API. Out of this Jupyter notebook, we need to have the account ID, authentication token, and then we can do things like query all the materials that have silicon, for example, as one of the elements present inside this material. This is a trivial example, but with the functionality of Python and the RESTful API, we can do much more. Here is the list of applications that we support today. Most of them come from the density functional theory perspective, like quantum espresso, VASP. We also support molecular dynamics on the infrastructure level, and we support things like MWChem, CP2K, Turbomol, and VM2K as well on the infrastructure level. We support analysis tools, visualization tools like VMD, XCrystal, and such. And of course, the scripting applications like Python. There are different access scenarios. We can go through the user interface, or we can bypass it and access the platform on the command line level. In that case, we will use the modules environment to set up the modules inside the command line. And we'll use the batch scripts to execute the calculations. Here's an example of a batch script for PBS. Here is a quick example of how we can access the command line. Command line can be accessed from the web. There's a web terminal that we can open from the right-hand sidebar. We can do pretty much everything that we would otherwise do in a SSH terminal out of this web terminal as well. Okay, so this is just a quick demonstration. So here is the midway summary about the platform overview. The exabyte-io platform is really, we see it as a comprehensive ecosystem for materials and chemicals R&D that is transitioning today's prevalent siloed or isolated approach to a fair, findable, accessible, interoperable, reusable infrastructure ready for the data-driven science. The goal of the platform is to supercharge computational sciences, the initial goal, by providing a dedicated environment to organize and accelerate the work that they do, and connect it with the data science units. The platform can be accessed on multiple levels: infrastructure for compute only, programmatic level, RESTful API, and the web interface. Now let's go and understand a little bit more about what is there under the hood. So I was speaking about the different components of the ecosystem. And I said that we have them implemented as open source repositories. And indeed, if you look at our GitHub page, you will see one-to-one correspondence. So there are standards that are implemented inside SE as a repository. The extractors, there is an example for it called exaparser. And we have an application called Materials Designer written in JavaScript that also represents this open source component. And we also have examples for communication with our RESTful API that users can adopt. We start by identifying the entities that we deal with. And this quick diagram demonstrates the way that we see these entities and how they are connected with each other. We start with material structures, and there are certain properties that characterize these material structures. And we have also a workflow that can produce another property through a job. So our simulation jobs produces a characteristic property as well that can be attached to the original material. This initial set of properties just classify the structure. It could be crystal lattice and crystal basis, for example. And this final property is something that is extracted by the calculation. And there is a certain precision associated with each of these properties that will help us store and organize this information in a database. We separate these entities on purpose to improve the modularity and cover different multiple use cases and different kinds of material types. Here is how we implement the data structures. We base the data structures implementation on JSON, JavaScript object notation format. And we organize them as schemas that define the data components and their relationships. So if you look at the schemas a bit more in details, you'll see that here's an example schema for a material. It contains a certain set of keys or properties. That includes things like formula, crystal basis, crystal lattice. And if you look at the example or representation of this material schema for silicon, FCC silicon, we'll see that the basis is the key that contains coordinates inside it. And we have coordinates indexed by ID and the corresponding elements at each of these coordinates also given here. So this is how we define the keys and their types of data that is stored under these keys. And this is how we actually implement a particular material as an example. Now, why it's important to understand all of that? It's important to understand this because in some cases, the user interface doesn't necessarily provide the functionality that is desired sometimes, but we can always go under the hood and we can always see the original data. Here is an example. If you look at the material and we expand it, we will be able to see the original JSON data structure with lattice and basis inside it. So every entity that user encounters inside the platform is defined inside the exabyte data convention and is available as an open source GitHub repository. These definitions are meant as a unified format to incorporate data from multiple different material types. Now we support the crystal materials for the most part. In the future, we plan to support molecules and nanostructures as well, and different modeling applications like density functional theory today and molecular dynamics, Monte Carlo, and such in the future. The platform provides different kinds of access levels, including user interface, remote desktop, command line, RESTful API. We welcome the contributions. So we on purpose made parts of the infrastructure to be open source. So anybody can fork the repository and put a pull request on GitHub. So here's an example pull request where our partners helped us introduce additional functionality to the materials designer interface. And of course, people ask why would they contribute? We have certain ways to compensate the users, to compensate the people who contribute actively. And then it's always good to see your contributions online. It's always good to see other people using it. So let's look a little bit at the user interface and its main components. There are 5 main components of the basic user interface, the generic user interface. That starts with the header at the top, the left-hand sidebar, the right-hand sidebar, the footer at the bottom, and the support widget. And let's speak a bit more about the support widget, because that's the most important component in the beginning. This is how it looks like. So whenever you are logged in into the platform and you experience any kind of problem or just need more clarification, we advise you to submit a support request. And there's minimal information that has to be provided, but we really strongly encourage people to use screenshots or even better screencasts, because it really explains the problem to us in much more detail than just the explanation, the textual explanation. There is also an interactive chat in the bottom right corner, but it's only meant for the people who are not logged in yet, for those who are considering our platform, for those who need assistance with the registration. And for the logged in users, for the people who have been on the platform for quite a while already, we help through this support chat in the lab. Now let's look at the other main components, and let's start with the left-hand sidebar. To open the left-hand sidebar, we click on the top left corner, and here we can navigate to the entities that this account owns, right? Like calculation jobs, materials, simulation workflows, and such. In the right-hand sidebar, we have the collection of administrative items. So to open the right-hand sidebar, oops, I apologize, let's go back. Yeah, to open the right-hand sidebar, we need to click on the account name at the top. And we will be able to navigate to the list of our payments from, for example, from the past, or to the account preferences, or we can open the terminal or remote desktop sessions from here as well. Now, besides the generic UI entities, we also have UI components. We have the entity-related interface components. So interface components that hold the information about materials, simulation workflows, or calculations. And we have three different kinds of this entity-related interface components. Explorers, or the list table or list component for exploring the entities inside a collection. A designer component to modify, edit, develop the entities. And a viewer component to visualize one or more entities and to make small adjustments, such as edit the metadata. So here is how an example entity explorer looks like. It's simply a table that shows which entities are present, in this case materials, inside our account collection. And it has certain actions that we can perform on these entities. The actions that are collective, that can be applied to multiple entities, are at the top. And the actions per each entity are here, given per each item in the dropdown. There is a way to search through the entities and filter them in the top. And here is how the entity designer looks like. So this is an example designer component for materials. And again, it has certain menu items at the top. It has a list of items on the left. It has a crystallographic panel for the case of materials in this case, and 3D interactive crystal viewer on the right. And this is how the entity viewer looks for materials as well. Here we can visualize the material structure, and we cannot edit it. We can only edit the tags and the material name. So the metadata that is associated with this material, and we cannot edit the material itself. So let's speak a little bit about the accounts very briefly. Accounts own and perform actions on the entities. Accounts define the different ways of how users can interact with the platform. For example, as a person, I can have my personal account, and I can also be a member of a team account for exabyte-io. And when I'm working under my account, I work out of my personal perspective, and when I'm working under the team account or the company account, I contribute to its intellectual property in a way. And there are organizational and personal accounts. Personal accounts have only one member, the person themselves. And the organizational or team accounts have teams that have different permissions. So as an administrator of an account, I can dedicate certain kinds of permissions to the account members and allow them to read or edit the entities. So to see materials information or to edit materials information as well. Account members have shared access to these entities as set by account administrators. Now, an important concept that we introduce is the concept of the entity bank. So the collection of entities that the account owns contributes to as we call it, the entity collection, right? And the unique entities are collected inside the bank through this mapping operation. For example, let's say we have multiple users, multiple accounts that each have Silicon FCC as the material that they own, right? And all of this Silicon structures will map into a single entry inside the materials bank collection. And we know that they map into it by having this exabyte.id property inside the collection item that maps to the ID inside the bank. When the account has private data enabled for it, nobody else but the account itself can see the entry inside the bank. And when there is no private data, when there's the data is public for this account, and other accounts also are able to see the information created inside the entity bank. There is a way to import entities from bank. There is a dedicated action in the list of workflows and materials that can take us to see the bank items and import them and copy them. I will explain how to do that momentarily. And we recommend users to import the entities that are created by the curator's account, because those are the entities that we curate. We make sure that they are high quality and there is no confusion there. The tags and then the flags are properly set inside the calculation files. Let's speak briefly about the service levels now. The service levels define the features that are available to accounts. And we have really 4 different kinds of service levels, starting from free, which is a no commitment service level. Accessing the platform is free and always will be free. We also provide users with initial credits to try the paid calculations. And once they're ready to commit and submit and transition to a paid service level, Pro is a good example for an individual users, right? When you don't need to share the data with anybody else, you can subscribe for the Pro level. Team is good for smaller teams, and Enterprise is good for larger organizations, for people willing to collaborate with multiple other users. And we have different kinds of features available to these different kinds of service levels. That includes things like the amount of disk space, the severity of the support that we provide them, how quickly we reply to support tickets. We try to reply as quickly as possible, but there are certain obligations that we have, and it depends on the service level. The number of account members per account, the availability of private clusters, command line access, and such. All these are different for different service levels. So let's summarize here about the core components of the platform. Again, we start with the data standards and define the entities that platform works with through multiple different access scenarios. These definitions are meant as a unified format, and we encourage participation from you, from third parties, in helping us evolve this unified format and helping us introduce new functionality. The platform provides a user interface to work with the entities and gives alternative ways to access the data, to access the computational capabilities through RESTful API and remote desktop. The accounts can perform actions on the entities in a shared access way, allowing users to collaborate. And features that are available to accounts are defined by the current service levels, from free to enterprise. think we are halfway through right now with the basics of the platform and the core capabilities covered. Are there any questions? It does not seem so. Let's see. Okay, there is one question. What is an entity in a general sense? So the entity and the way that we think about it, let me get back to its representation. It's just a concept, right? A concept that we identify that materials R&D is dealing with. It's a concept that is clearly defined and has a data structured representation in a database. So material has a definition, it's a material structure. So once we have a structural information that clearly identifies a material, we can store the information for it inside a database, and that's what we call an entity. The workflow is a logical flow of certain small calculations that we need to execute to extract a certain property. Right? So entities really are concepts that can be clearly defined, and they can hold data representation inside a database. Okay, if we can speak about this more at the end of the webinar, we can even have a discussion, but for now I'm going to proceed if there are no other questions to discuss materials. Okay. So material is an entity, and we have certain actions that are available to deal with this entity. And usually people start with uploading the information about materials that they already work with. And here is how you can do that, right? We can navigate to the list of materials, click on the upload action, and select one or more files from the disk. In this case, I'm using postcard files in a .wasp extension. Excuse me. And we select these files and click OK. So here is a preliminary list where we can further edit, review, or edit the information. And in this case, I'm going to tag one of these files and add 2 tags to it, tag 1 and tag 2. So we can see that this particular entry will be tagged with this metadata. And now I'm selecting all of the entries and I'm clicking upload to actually upload this information. And I'm seeing that all of them are uploaded. This is a confirmation. And at the end, we see that these 3 materials files now contribute to the materials entities inside the database. And one of the entities, one of the entries in the database now has the metadata in the form of 2 tags. Okay. Now, the second option is to import materials, information material structures from an online database. And today we support materials project as the source. So we can click on the import action at the top and search for the material that you would like to upload. You can notice that there is only 3,000 material structures listed here, although materials project supports much more. The reason is that we do not source all the materials that materials project has inside its database. We only cache the ones that our users have imported before. So previously, our users have imported about 3,000 different materials, and that's what we hold in a cache to avoid hitting their APIs too frequently. So when you search for a material that is not in the cache, we still ask for it from the materials project API itself. So in this case, magnesium oxide is already present here, and I can select the entry and click import to add it to my account collection. And we also use the tags that materials project has in this case to assign them to the account entity. All right, and if we click on it, we can visualize the structure and make sure that that's the one that we wanted to import. Now, a third option is to copy the information from materials bank. As we proceed and have more and more people on the platform, they create material structures and more information within our platform. And the likelihood is that some other person have already worked with the material of your choice if you are a new user. So you can navigate to the materials bank by opening the left-hand sidebar, clicking on bank and materials, and searching for the structures just like we did in the previous example. So here is a magnesium oxide. I can click on it and click copy. And then when I come back to the list of materials for my account, I have this entity and this entry copied to my collection. Okay, so that's the third option. There is also a quick shortcut to navigate to bank here in the list of materials actions. Sometimes the regular search is not enough, and we need a more advanced capability. And to do that, we have implemented the advanced search, which is a search with the arrow. And when we click on it, we are presented with the query builder. Here, we can construct a sophisticated query using AND and OR logical operators. And here I'm demonstrating how we can do that and filter the list of materials by formula that contains aluminum, by the unit cell volume that is less than 80 angstrom cubed. We measure the distances in angstroms, and by adding the tags that contain high pressure. So if we now execute this search query, we see that there is only one material that corresponds to it, and that's how we can do the advanced search within the account collection. And if you reset it, we get back to the full list. As the number of materials grows in the collection, it's convenient to use this functionality to narrow down the items. Now, let's speak briefly about the materials designer. To open the materials designer, we click on the create button. And I briefly explained already how it looks. There is a header menu with multiple menu options. There is a list of currently present items within the materials designer session. There is a crystallographic panel, and there is a 3D interactive viewer. Materials designer is a standalone open source JavaScript application. So the functionality that it supports can be extended through your contribution as well. And it can be used in any third-party projects as long as they're on the web. So here is an example of how we can select materials within the materials design. We would open the input-output menu, click on import, and here we are presented with the list of materials inside our account collection. So in order to have any materials here, we have to have imported, uploaded, or copied from the bank the materials in the past, right? We have to have something inside our collection already. And then we can select it, search for the exact material, and select it to make it available inside the materials designer session. By default, we add the default material into the session. At least one material has to be there, so we add the default material by default. And we can remove it by clicking on the remove button here. And that's how we focus on this newly imported material structures. Okay. There is much more functionality available within the materials designer, but I can't cover it in the short webinar. So if you have any questions, we can speak about those separately. Now I will proceed and explain the basics, the basic actions for workflows. Just like with materials, we have the workflows bank. And as many more people join our platform, we have many more workflows inside the bank. And here is how we can import one. We click on bank and workflows, and we search for a particular property that we'd like to be extracted within this workflow. We can also search for the application. We can search for the subworkflow name or tags in case of the account collection. And then we select this workflow item and click on copy. And that's how we can copy this workflow into our private account collection. It's usually handy to start with the workflows that are created by curators, because again, we maintain the quality of these workflows. And if you need to modify it, it's easy to do that using the workflow designer. But to understand how to use it, let's first understand the inner structure of workflows. And it really consists of two subcomponents, the subworkflows and units. So subworkflow is a set of distinct units or primitive calculations that are combined together in a flowchart. And each subworkflow is specific to a single simulation engine. So if we use, VASP or Quantum Espresso, then a subworkflow can only contain one application. It can only be related to Quantum Espresso. While the workflow can contain multiple different kinds of simulation engines. Subworkflows must also contain a single model, such as density functional theory, and a single method, such as a pseudopotential method. This concept is introduced for modularity and to reuse the commonly utilized logic. Units are elementary calculations, and unit is executed in a certain succession, in a certain order, inside the subworkflow. And we can have different kinds of unit to facilitate the logical conditions, to facilitate things like MapReduce. Units have types. For example, the Quantum Espresso run would be an execution unit, and there could also be an assignment unit when we set a certain variable to a certain value. Execution units in particular have executables, such as pw.x, the runtime executable of Quantum Espresso, and flavors, such as pw, SCF, standing for self-consistent field. Again, this is made for modularity and reusability. So we can reuse the pw SCF unit in multiple different workflows and subworkflows. And here is how the workflow designer itself looks. Again, we have the header menu with the name of the workflow and basic metadata. On the left, we have the items list with multiple subworkflows. And on the right, we have the subworkflow editor. Here is how we can add a subworkflow to a workflow. We click on the plus button, click on append, and we can switch between these two. The newly added workflow, subworkflow is empty. We have to also add units to it. And we can do that through this subworkflow editor. We have the actions menu bar, and we have the editor tabs here, and the units flowchart. And here is where we can add and edit the units. So this is the units flowchart zoomed in. The currently active unit box is highlighted in gray, and unit type is shown by the first letter. So E means execution unit, and A means assignment unit, C means the convergence unit. This might be a bit misleading as of right now. So understanding the exact logic might be difficult. This is due to the current implementation, but really the flowchart on the left represents the convergence flowchart. So we can start with a certain number of key points and then save the previous result and then execute the PWSCF calculation and figure out whether we have reached the convergence in a logical condition. And if we didn't, we will increment the number of key points by 1 and rerun this again. So this flowchart actually is identical to the flowchart on the right. And once we open a particular unit, we can see its detailed view as demonstrated here. We can see the application section, the properties section, the monitor section, information about the previous and the next unit, and the input templates, the textual templates that contain the input file for this unit. The application section is important because that's where we have the executable and the flavor information for it. Speaking about the templates, that's what computational scientists are familiar with. But what they might not be familiar with is the language that we use to facilitate the templating. We use Jinja, which is the Python Pythonic templating language. And instead of storing the textual information inside the database, we store the templates. And then we combine these templates with the materials data and the data coming from the workflow properties, right? So in this case, we have materials data that contains the structural information, like the atomic positions, the cell parameters, atomic species, and this materials information comes from materials entry in the database itself. So when we go to the preview tab, we will see the information rendered. So in the template, we see the template variables. In the preview tab, we see the actual materials information. And we can have it for multiple materials at once when we have multiple multi-material jobs. You can also notice that some of the variables are not rendered. And that's because we have two moments when we render this template. The first happens on the web, and the second happens during the calculation. There is really no need for the users to understand beforehand which job directory this calculation will be executed in. This is a system property that is rendered during the second runtime render. This is also where we can do things like convergence studies and increment the variables, because we can substitute the rendering context at the time of execution. So the second time render is what facilitates the advanced logic during the execution. Okay, let's proceed to discuss the jobs now. So once we have a material and once we have a workflow, we now can create a calculation or a simulation job. And it's important to understand that we have to have this material and workflow information before creating a job. We have to have enough balance to perform the calculation, and we need to have enough disk space or disk quota to perform this calculation as well. Then we can navigate to the desired project, which is the collection of jobs. We use projects to group together jobs that relate to a certain particular scientific project, like a study of a particular material set, and for the accounting properties too. Each project has its own dedicated accounting channel. Or for the simplest case, we can just click on select on create job inside the left-hand sidebar, which will take us to the job designer. And here is the basic outline of the job designer. It contains the materials tab, the workflows tab, and the compute tab. And at the top, it has the header menu with the name of the job and the drop-down for actions. The first step in creating the job is to select materials. And here's how we can do that. We click on the drop-down and header, and then we click on select materials. And we can select one or multiple entries. Right, in this case, I'm selecting 6 entries, and all of these 6 materials will be available inside the job designer. And as you can note at the top here, we now have the formula ginger variable inside the name of this job, which will be automatically populated based on the formula of this material. So for high throughput calculations, it's especially handy. So once we create multiple jobs out of this job designer session, each one will have the formula attached to the name so we can quickly find them. Okay. So we can preview material structures so you can cycle through them to make sure that these are the materials that we want to work with. The second step is when we select a workflow. And we can only select a single workflow, multiple materials, but a single workflow. And we select the workflow from the account-owned collection. So we select the item here, click on select items at the top, and now we apply this workflow to this material through this job designer. The third step is to set up the computational parameters. And this could be quite a bit complicated depending on the simulation engine and the type of workflow that we deploy. But the basic parameters here are the time limit. So the time limit that we give to this calculation, it will not proceed beyond this time limit. The calculation infrastructure, we support multiple cloud providers. There's multiple clusters. The kind of queue, resource management queue that we want to support submit this to. For example, the debug queue is meant for very quick turnaround, but limited resources. The ordinary queues are where the bulk of the calculations would happen, and the fast queues are meant for high throughput, multiple parallel calculations running at the same time. There are certain notification options, like you'll get an email when the job is started or aborted or ended. And there is a certain set of advanced options as well. Next, we click on Save in the header to save the job. And that's how we create a calculation. There is a couple of notes that I wanted to speak about regarding the job creation. First, we do not allow users to modify the workflows during the job creation. We do that on purpose to assert data consistency. There is a way to modify and edit the workflows first. So if you have a certain kind of workflow, then you should first edit the workflow before coming to the job designer. There is a way to modify the input preview directly inside the job designer, but just so that we cannot always think about all different cases when users need to do that, right? Sometimes you do need to modify the input files, and you can do that by modifying the preview directly. But we suggest this to be avoided, again, to assert the data consistency. Multiple materials can be selected for high throughput calculations, or as a second option, multiple materials can correspond to multi-material jobs, such as MEB calculations for chemical reactions, when we actually looking at multiple images of the chemical reaction. Jobs can also span other jobs and wait for their execution, but that's a topic that we can discuss in the advanced topic seminar. So once we have created a job, we can run it. And to do that, we select the entry in the list and click on Run. Now the status is changed from P, which is pre-submission, to S, which is submitted. And shortly, it will proceed to be A, which means active. Each of the statuses are color-coded to be easily understood. And here we can see how long the job has been waiting for and how long it was executed for when the job is finished. We can navigate into the running calculation here to see which unit is currently active and navigate into the unit to see its output text, to visualize the convergence in real time. Okay. And when the job is done, the status of the job is changed to finished, colored in green. And when we open the job, in that case, we see 2 extra tabs added to the job viewer. In this case, it's results and files. Results are structured and grouped by unit. So band structure is the workflow and PWSCF is the unit. And these are the properties that are extracted out of this unit, such as total energy, pressure, Fermi energy, total force, and such. The band structure plot is extracted out of the bands unit and also presented here. Navigating to the Files tab allows us to access the files. We can either visualize the files on the web or we can download and see them on our own computer. Okay, so here is a summary of how we can deal with materials, workflows, and jobs. And now it's time for us to get back to the Q&A and answer any questions. Okay, there was the first question about the entities that we already answered. There's another question about, can we design a new material whose atoms are not present separately in material bank? I guess the question is about whether we can avoid adding a material to materials bank. And the answer is no. So we always propagate the information into the materials bank. But Let me get back to this explanation. Just give me a moment here. But as I explained here, the information, whenever the account has the private data enabled for it and activated as part of its service level, nobody else but the account itself can see this materials bank entry. So the reason why we always create this mapping is because the entry inside this bank is actually what we use to associate materials properties with. Because there's multiple different properties and they have to be associated with unique entries, we have to have this unique entry to associate these properties with. But this entry does not necessarily have to be visible to anybody else but the account that had created it. There could be a case when two accounts independently have created a particular structure. And in this case, only these two accounts, if they're both private, will be able to see this entry. But the account that have created this structure first will technically be the owner. Okay. There is a question about VASP. Is VASP key required? I guess the question is VASP license required? Yes, absolutely. We at this point we only support VASP for users who already have a license purchased, and we have certain flexibility for the academic accounts, but for the enterprise accounts, it's only for the people who already own the license. And there is another question about, do you support only QE and VASP? And the answer is yes, we support only QE and VASP at the level of the infrastructure. So if you look back in here, there are different types of access to the platform, right? Through the user interface, through the RESTful API, through command line. So through the user interface, which is number 1 here, we support only Quantum Espresso and VASP. So this is the most developed, well-developed, the most well-integrated engines today. On the infrastructure level, through command line, we support LAMPS and NWChem as well, CP2K, GROMACS, and TurboMol and VM2K. And through remote desktop, we support, of course, all of this through remote desktop terminal, and through the graphical interface, we support TurboMol in this case. There is another question about how do you compare to the AIDA? How do you compare to the MathCloud platform? I guess this question will require us to go into more details to discuss this. But in short, I think the implementation that we speak about, the implementation that is focused on the data structures, is what's unique to our platform. So really focusing on structuring the data first, and then instead of implementing the workflows inside Python scripts, for example, as AIDA does it, I'm not entirely familiar with how MathCloud does it. I've heard about the platform, but I'm not familiar with how it operates. But most of the time when computational scientists deal with simulations, they implement the workflows inside code, right? So they have Python code that implements a particular calculation. And that's a good way to deal with it, and it's definitely reusable, but it's hard to search through the metadata that is associated with this calculation. It is hard to see the logic that is included into the calculation flow. And as I explained here, we have a way to store the logical information inside the database too. So the workflows in our case are data structures that contain a set of subworkflows and units. And that is how we make sure that we store the information about the workflows logic too. I hope that's clear. If not, we can discuss it separately. Okay, I think we have went through most of the questions here. Anybody else wants to ask a quick question? Maybe within the next minute or two. Okay, if not, please feel free to shoot me an email if you want to discuss things further. I'm at timur@exabyte.io. Again, thanks everybody for joining, and my best wishes to you to stay safe as we battle the coronavirus. Thank you very much, and have a good rest of your day.